presents Educational Satellite Television Programs.
Hello, teacher. Hello, students. Welcome to today's lesson on forces and Newton's laws of motion. Previously, we discussed Newton's third law of motion and the law of conservation of momentum. We introduced many of the core equations necessary to solve problems related to momentum. Today, we will put the lessons we have learned into practice. We will start by using the law of conservation of linear momentum to work through some different scenarios. If you are ready, we will begin. First, let us reintroduce the equation for linear momentum. Linear momentum is equal to mass times velocity. Let us try using this equation. Are you ready for an activity? This rhino is running at top speed. Its momentum is very high, and therefore, it is very difficult to stop. Let us assume the mass of this rhino is 1,000 kilograms. The rhino is moving at a speed of 18 meters per second. Can you determine the momentum of the rhino?
Students, let's get ready. Begin. Time's up! Let's get back to our lesson.
Welcome back, everyone. Let us find out the magnitude of linear momentum of the rhino together. We begin by stating the principal equation that will be used. In this case, it is P equals m times v. Then, we substitute the appropriate values into the equation for mass and velocity. Once calculated, we obtain the result. The magnitude of linear momentum of the rhino is 18,000 kilogram meters per second. Were you able to find the answer, students? If so, excellent work. As we previously mentioned, momentum is a vector quantity. This means the direction of motion of the object is also very important. These two trains are headed for a collision. What will happen if they collide? Both trains possess the same mass, which is 22,000 kilograms. Each is also moving at the same speed. The velocity of each is 20 meters per second. To calculate the total momentum of both trains, we must consider each separately to resolve their momentum. We will begin with the train on the left. The momentum is once again given by P is equal to m times v. But we will add a subscript to each letter to differentiate between the two trains. Thus, P sub A is equal to 22,000 kilograms times 20 meters per second. Therefore, the momentum of the first train is 440,000 kilogram meters per second. It is traveling to the right. Because the trains are moving at the same speed and possess the same mass, the result of our equation for the second train is the same, except for the fact that the train travels to the left instead of the right. Because the momentum of the second train directly opposes the first, we may write this value as a negative. It is important to remember this fact, as it will affect the solution. The total momentum in this case would be 0 kilogram meters per second. Remember that the law of conservation of momentum states, in a closed system, the total linear momentum must remain constant. This means that when objects collide, the total linear momentum before the collision must equal the linear momentum after the collision. This is only as long as there are no external forces acting on the system. In symbolic terms, this is expressed as sigma p sub initial is equal to sigma p sub final. Let us consider this example with an activity. Two balls are positioned on a flat plane. One of the balls has a mass of 8 kilograms and is traveling 12 meters a second in the direction of the other ball, which possesses a mass of 4 kilograms and remains stationary. First, determine the momentum of the system. Then, list some possible outcomes that could occur once the two balls have collided. Please get started.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
We are ready to continue, everyone. First, let us determine the momentum of the system. To begin, we can conclude that the momentum of the second ball is 0 kilogram meters per second. To calculate the momentum, we use the equation P sub A is equal to M sub A times V sub A. We then substitute the values of mass and velocity belonging to the moving ball. Thus, the ball is moving 96 kilogram meters per second to the right. This is the total momentum before the collision. Based on the law of conservation of momentum, we know that the momentum after the collision must also equal 10 kilogram meters per second to the right. There are thousands of potential outcomes once the two objects have collided, but in all instances, the linear momentum of the system is conserved. This means that once the moving ball hits the stationary ball may begin to move while the other stops. Since we know the total momentum of the system is 10 kilogram meters per second, we can establish the velocity of the second ball. Depending on the material, it is also possible that the balls may stick together. They may even move in the same direction once they are connected. In this case, the momentum of the system is still conserved. In this case, however, we calculate the velocity based on the combined mass of both balls, which is 3 kilograms. Another probable outcome is that the balls collide and then move away in opposing directions. Just like the other examples, the momentum of the system is conserved. This time, the balls each have momentum respectively. This concludes today's lesson. We have applied the law of conservation of momentum to solve problems. I trust you have found this informative. Until next time, thank you, teacher. Thank you, students.